Hello everyone. Okay, this video we are going to still continue talk about the false oscillation. Okay, yeah, there are a lot of things behind the false oscillation. Okay, so and in the previous video we discussed the when the applied frequency is away from your natural frequency, what will happen, right? Let me, yeah, where's my pen? Okay. And in the previous video, it say, okay, we have two situation is when we discuss two situation, omega is way smaller than omega zero and omega is way larger than omega zero. And when your omega is way smaller than natural frequency, your omega is almost also like a constant, right? Amplitude also as a constant. But when you apply very large frequency into a system, your amplitude is probably is 1 over omega square. Okay, that means it's decreased. That means your omega apply frequency increase, but your amplitude decrease. Okay, and this video we are going to show, okay, what happened when omega close to the omega zero. Okay, and there's a very real experiment for this, but in this video just skip this. Okay, and okay, so what happened when you apply frequency equal to natural frequency? Okay, that's we want to discuss in this video. And when you apply frequency equal to a natural frequency, in that situation, particular situation, we call this called resonance. Okay, resonance. Okay, at resonance, what will happen? At resonance, first of all, there is no lag between your applied frequency and natural frequency. Okay, you remember the formula for tangent alpha? Okay, let me copy this. Okay, tangent alpha is here. Okay, let me write down this. Maybe I should write down either right here. Our tangent alpha is equal to omega squared minus omega zero squared omega divided by tau. And our tangent also, there's another expression for a tangent alpha is resistance is denominator, reactance is numerator. Okay, so at resonance, omega equal to omega zero. Okay, omega equal to omega zero. So the tangent alpha, because omega equal to omega zero, so tangent alpha is become like zero. Okay, tangent alpha zero means m omega minus k over omega also zero. Okay, but actually you can check by this because omega equal to omega zero. So you can check this. You can check this m omega 0 minus k omega 0 and check if this is 0 or not. Okay, check by yourself. Okay, it's very easy to check by yourself. Okay. Okay, so at resonance, first of all, this is at resonance. This is a amplitude function and velocity function. Okay, and there's just, well, let's look at the velocity function. Okay, because velocity relate to energy very much. Okay, that's why we take a more focus on velocity. Velocity relate to energy very much, like kinetic energy and power, right? Remember the power, force times the velocity. So velocity relate to the energy and power very closely. Okay, and also kinetic energy. So velocity relate to energy and power very closely. Okay, so we see the velocity right now at the resonance. Okay, first of all, there is no lag, and the velocity is a function of cosine. And this cosine function is just equal to our applied force. We apply a F0, which is a constant, and times the cosine omega t function. That's our applied force. And you will find our applied force is a cosine omega t function, and our velocity right now is also a cosine omega t function at the resonance. So this just tell you at the resonance, your applied force and your velocity is at the same phase. Okay. So there is no lag because tangent phi is 0. That means there is no lag. So at this situation, your system will respond to the applied force very immediately. At resonance, your system responds to the applied force very immediately. Okay, and in that particular situation, okay, this graph is the amplitude function of omega. And in previous video, we mentioned a little about this. Okay, this graph is a over omega. Just draw the amplitude function as a function of driven frequency or applied frequency. And a omega is this one. Okay, don't forget about this. A omega is this one. Yeah, just right here. A omega is here. It's a very large, huge term. And you draw the graph as a function of applied frequency. You will get this function like this. Okay, and we will find after we draw this function, we will find at the resonance, the amplitude increase a lot. Okay, maybe I think maybe it's here. Maybe how to draw it very accurate. Yeah, this is a natural frequency. At natural frequency, you will find amplitude has very large value. Okay, that's what happened and resonance. At the resonance, you apply force and velocity at the same phase. Okay, that means there is no lag. Your system responds to the applied force immediately. And also you can think another way. The system just take all the energy. Okay, you apply input energy in the system, you input the energy into your system, and your system just take it immediately. Okay, so that's what happened at resonance. Yeah, velocity and force in the same phase, and that also means you apply the force into a system, apply energy into a system, and your system just take it immediately, and there is no lag. Your system just suck up all the energy, and in that so that because the system suck up all the energy, that's why its amplitude just shoot up to a very high value. Okay, so we just look more closely to the amplitude function and the resonance. Okay, and you will find a damping parameter B here, control the amplitude at the resonance. Okay, like the graph here. Here's the three different damping parameter. Damping parameter equal to 0, 2, 0, 8, and 2.0. Okay, when we have a large damp parameter like for this one 2.0, and you will find the amplitude doesn't increase that much at resonance. But when we switch the damping parameter switch the damping parameter to 0.2, for the red line, you will find its amplitude increase so much at a close resonance, and then decrease as a function of applied frequency. So this just what we see on this on the mathematical formula. The damping parameter B controls amplitude at the resonance. Yes, I think this very intuitively. You have large damp force, of course, you will have smaller amplitude. If you have very low damping force, so at the resonance you have very large amplitude because you have very few, you have the small or low resistance, right? Small damping parameter means the slow resistance. Okay, so this is very interesting, and this resonance happens in every aspect of science and engineering. Okay, it happens a lot. Okay, next slide just introduce some example. So this is an example for so the MIT. They do an experiment. They apply a frequency, okay, some wave and sound wave to the glass, and they keep increasing the frequency. At a particular frequency, you will find the glass just shaking like crazy, and then at a certain applied frequency, this glass just break. This just break, and that's called resonance. Because, like I say, the system take up all your applied energy. Okay, and the resonance, the system suck up your all applied energy. So these things happen in this glass, in this glass. At the resonance frequency, this glass just take all the energy from the sound wave. Okay, and there will be a large amplitude between atoms. Okay, large amplitude between atoms, and then your material just break. Okay, you can just look at this video. It's very interesting experiment. That's the resonance. Okay. And also the resonance, yeah, that's also resonance. Yeah, but I will just skip this slide. I will explain how the mass damper working in the building, but I will skip this slide in this video. I just go a little further because I want to talk about the resonance more. And the resonance also happen at the molecular level, because the vibrational motion is just like a simple harmonic oscillation. Your vibrational motion corresponding to frequency, and when your molecule doing rotational motion, think about the very simple rotational motion, and it's called uniform circular motion. In the uniform circular motion, you are doing rotation. You also have the frequency, right? Maybe accurate, the most accurate is angular frequency, but doesn't matter. It's just a frequency, okay? And maybe you heard some quantum mechanics. You see the molecule has an energy level in there, in the energy level in molecule, and the energy transition and electronic transition in between energy level also corresponding to frequency. Why? Because I think most of you heard about the light quanta theory. E equal to h nu. H is a Planck constant, and nu is a frequency. So electronic transition in energy level also corresponding to a frequency. Rotational motion also corresponds to frequency. Vibrational motion also corresponds to frequency. And electromagnetic wave, electromagnetic wave, okay, because it's a wave, so it's also corresponded to a frequency. Yeah, wave has a frequency, right? Remember that in your high school physics, wave also a frequency. So also, and we apply electromagnetic wave into your molecule. Yeah, this is applied frequency. Electromagnetism, you apply a frequency into your system. When applied frequency equal to the vibrational frequency, or the input applied frequency equal to the rotational frequency, or the applied frequency of electromagnetic wave equal to the frequency for electronic transition, at that moment, resonance happen. Resonance happen, the molecule just suck up all your energy and do absorption. Okay, absorption apply energy from electromagnetic wave, and then this we call absorption spectrum. We call it absorption spectrum. The applied frequency equal to the vibrational frequency of the system, or rotational frequency of the system, or electronic energy transition frequency of the system, and then resonance happens, and the molecules take up your energy, all your energy, and become absorption spectrum. And here is an example for absorption spectrum. Yeah, this actually you will learn this after all. Okay, just give you some example. This example is IR spectrum is corresponding to vibrational motion, and the microwave spectrum is corresponding to rotational motion, and UVV spectrum of a molecule is corresponding to energy transition between the energy level. Okay, this has an energy transition. Energy level has a frequency, rotation level has a natural frequency, and vibrational motion has a natural frequency, and your input electromagnetic wave has a applied frequency. And the applied frequency equal to this natural frequency. It just has the spectrum. It will absorb the energy. See, just absorb the energy here. Yeah, absorb the energy. Let's see here. You see this spectrum here is a peak absorption energy, and there's also a lot of peak in small layer. There's also absorption energy, and here is a peak absorption of energy, and here is another peak absorption of energy. And just look back. Just looks back our previous picture here. And at the frequency close to natural frequency, you have a peak, absorption peak here. That means systems suck up your all input energy. Okay, and we get absorption spectrum. Okay, same thing here. Okay, so actually the force oscillation not only happen in macroscopic world. Okay, no, oh, sorry, not the force oscillation. The resonance phenomenon not only happen in macroscopic world, it also happen in microscopic world. Okay, so the resonance is happens in every field in science and engineering, and that's why the force oscillation is so important. But I don't know why the force oscillation in general physics textbook the force oscillation only just one page. Okay, I don't know why, but because it's very important phenomenon. It's across every field. Okay, so let's in this video we just discuss what happened at the resonance, and there's a small section left. Left is called Q factors, and I think I believe I will just mention Q factor in the next video because very simple, yeah, just very few. But for this video, I just focus on the resonance. And okay, so this is my explanation for resonance. Okay, so I just start video here, hoping you can get more understanding for the resonance. Okay, see you in the next video. Bye bye. Mm-hmm. Yeah, it's kind of also very long, I think, 60 minutes. Mm.